Welcome to a lesson with Dr. Powell. Let's take a look at how we can make a well-defined map from Z that preserves addition between the groups Z mod 6 and Z mod 10. Let's represent the elements of Z mod 6 as 0 bar, 1 bar, 2 bar, 3 bar, 4 bar, and 5 bar. This represents 0 bar represents all of the integers that are multiples of 6. 1 bar represents all the integers that are 1 more than a multiple of 6, 2 more than a multiple of 6, 3 more, and so forth. We partition the whole set of integers into chunks. And we can represent the group elements this way, and they add very nicely. Something that's 2 more than a multiple of 6 plus something that's 3 more than a multiple of 6 is something that's 5 more than a multiple of 6. Something that's 4 more than a multiple of 6 plus something that's 5 more than a multiple of 6 is something that is 9 more than a multiple of 6, which is equivalent to 3 more than a multiple of 6. So you have a nice defined addition. This forms into a group. Similarly, we can take different bars over here, but we'll use a notation of double bar just to distinguish from over here. And it goes all the way down to 9 double bar. So we want to create a map that is a function that's well defined from Z and that preserves addition. Well defined from Z, what does that mean? Well, that means if I take anything in here, the way I'm going to describe my map, if I take anything in this chunk, meaning anything that represents 0 bar at all, any A that represents 0 bar, so for instance, 12 bar is another representative of 0 bar. So even if I took 12 as my beginning number and did something with it, and got something over here in my image, call it B, and took a double bar of it, that should be the same result no matter what. This should be the same chunk in the image no matter what representative I chose for 0 bar. Now, in doing this, pretty much what that means is well defined from Z. Any representative in here has to be sent to the exact same chunk over here, meaning this whole chunk simply needs to be sent to a whole chunk over here. 0 bar needs to land inside of one of these chunks via F. So the image of everything in 0 bar as a subset of Z has to live completely inside of something over here in the image. What is it going to live inside? Well, it preserves addition. One of the properties of a function that preserves addition is that an additive identity needs to be sent to an additive identity. So in particular, that means that we need f of 0 bar to be completely contained in 0 double bar. Now, also, let's take a look at this idea of preserves addition a little bit and take a look at something like this. What is this going to be? Well, since addition is preserved, this is going to end up looking like something like this. Addition of the in the domain turns into addition in the codomain after we take images of each domain element individually in particular, and then we add them up as follows. Notice that this is simply just tripling f of 1 bar. Likewise, you can imagine, even if you take like 5 bar, that's 1 bar plus 1 bar plus 1 bar plus 1 bar plus 1 bar, and that's going to be 5 times f of 1 bar. You notice that anything we do, it's like we're multiplying by f of 1 bar. So because of that, preserving addition, at least between these groups, is going to just be represented by a multiplication. So we're multiplying things. In fact, that even extends to what's happening in Z. A multiplication is happening. Let's look at a number line and consider 0 bar, which just looks like multiples of 6, 0, 6, 12, 18, 24, and 30. Now let's consider multiples of 10. So 10, 20, and it lines up right here with 30. Okay, so these numbers represent 0 double bar, and these ones up here represent 0 bar. Is there something we can multiply all the elements of 0 bar by so that they end up landing in this schematic for 0 double bar? Well, notice if you multiply them all by 5, the 6 would be right here. Notice you can see that because it's the first time they actually match up. 12 would actually be twice what we just did, so you'd be at 30, and so past 30, so double 30 to be at 60, and so forth. 18 would land at 90, all we're doing is multiplying by 5. So notice if we define a function as follows: f of x bar is equal to double bar 5x, at least in the case of 0 bar, this works very well defined, because any element in 0 bar can be represented as x bar, such as 6, 12, 18, 24. This will naturally always land us in 0 double bar. So far, so good. Well, what about the other ones? What about f of 1 bar? Does the same thing hold true? Do I really get f of 1 bar landing in just one thing over here? How is that going to work? Well, 1 bar is, you just take one more than a multiple of 6 everywhere. And then we're going to be taking these and multiplying them by 5 and see if they actually land in something that's one more than or not just one more, it could be anything more, but just so it lands in one coset or one chunk over here. So it lands in just one of them. That's all we need. We can do this computationally even. Let's see, if we take something that's 1 plus a multiple of 6, we multiply it by 5, we end up getting 5 plus a multiple of 30. Well, hey, a multiple of 30 is a multiple of 10, and we're going to be 5 more than a multiple of 10 every single time, only 5 more than a multiple of 10. Well, that's great, because that means that we actually land in 5 double bar just as expected. You'll notice that just preserving this first part is enough to guarantee that the rest is taken care of. If we're thinking about multiplication, in order to preserve addition. Because if we multiply this by something, such as 5, look what happens. So 5 will put this 6z to 30z, which is contained in 10z. And so whatever's left over here is just going to be a shift of that. So really all we needed to do was ensure that this was actually inside of the 0 of the image. This is called what I call the identity to identity criterion. We need the identity over here to map to the identity over here. And then if we force the definition of the function, so it must preserve addition, that ensures that the function will be well defined. All we need to really check and make sure of is that all the representatives that represent 0 over here are sent to all the representatives that that are represent 0 over here. Okay. So thanks for watching.